Hello physics students, welcome to part 3 of electric fields. This time we're going to talk about electric field strength. Now we have a formula for electric field strength. E equals F with a subscript E. Now we start using subscripts for force, this is force, just to tell us the difference between, say, force magnetic, force electric fields, or force gravity, things like that. So we have Fe divided by Q, where E is what we use for electric field strength. Its units are newtons per coulombs, or newton coulombs to the -1. This is the charge experiencing the force, and charge has coulombs as its unit, and of course force is in newtons. The magnitude of the electric field is defined as the force acting on a test unit charge. So that's another way of saying an imaginary charge placed at that point in the field. So the direction is given by the force direction if the unit charge is positive. So if our imaginary test charge is positive, that's the direction we would give to the electric field strength. And the units are newton coulombs, or newtons per coulombs. Electric field strength, there's our equation. So we have this. We also have Coulomb's law, F equals K Q1 Q2 on R squared. We can combine those and it gives us this, which is another measure of electric field strength. K, the electrostatic constant, Q, the charge causing it, and R squared, the charge causing the electric field, which is a very useful thing to have. And where does this one come from? Well, we've got this one. We rearrange E equals F on Q to being F times by 1 on Q. Substitute F for K Q1 Q2, where we've, instead of using Q1 Q2, we use capital Q and small q, and these q's, little q's, cancel. So we don't need a charge to work out the force in this case. We only need the charge causing the electric field. And so let's have a look at it. This is for non-uniform, so radial in other sense. We consider a point of positive charge here, Q plus. And if we put a positive test charge at different points, for example here, then forces of repulsion, because that's an imaginary positive charge, so the force would be that direction, and the electric field strength is given in that direction as well by KQ on D squared. If we wanted to know the force, we'd need to have a charge there as given by little q, and then we would use Coulomb's law. But when we are just interested in the electric field strength, we get a measure of it in newton coulombs. Okay, so slightly different formula depending on what we need to find out. If we want the electric field strength, we use E equals KQ on D squared. If we want to find the force that a charge is experiencing due to an electric field, we might use F equals KQ on D squared. Okay, and there's our formula again. Electric field strength, charge causing the electric field, and distance from the charge in meters. And we use K is an electrostatic constant. Now we reinforce this one because we're going to do magnetism shortly, and it has another constant which is given letter K, totally different value. This is a very large number, notice that, and therefore when we were using gravity, our gravitational constant was a very small number with a very similar equation, well, the one previous anyway. And notice that this is a very large number, and that shows you that electrostatic force or electric field forces, or the forces due to electric fields, act over very small distances but are very strong, and they become less strong as you move away from them, whereas gravity was the converse effectively. Let's consider a couple of examples, or one examples. Here we have A represented by a point, and it has a charge of 3.5 microcoulombs. so we use prefixes sometimes. They're on your information sheet. And we have B, which is positive also, 2.5 microcoulombs separated by 15 centimeters, and we want to determine the direction and magnitude of the electric field at point X here due to two positive charges, and we want to determine the point where it would be 0 along that line because the electric fields would cancel each other out. So there's the question again, and so effectively it's a vector sum question. So we imagine that one of the charges disappears and we just work out the electric field strength due to A, and it would be that value, and it would be towards B or away from A, and then we work out the electric field strength due to B, and that's towards A or away from B because again it's a positive charge that's causing the electric field, and then we use vector addition, defining one way as positive, one way as negative, and we get the answer. So you just have to be careful how you add and subtract all these sorts of things. But if you get your mind around it, draw yourself a diagram, you should be okay. And then determine the point where it's 0. Now this is a little bit harder and probably a little bit outside of our course. So what they did here is they said S is the distance from A, and so the distance from B is going to be 15 minus S. So you've got a line A and B, and if the point's there, we'll say this is S, so that must mean that 15 minus S is how far we're away from B. So that's how they worked it out there. A little bit of simultaneous equation, but we wouldn't expect you to do that sort of maths, but it doesn't hurt you to know it. So the next video is all about electrical potentials. So I hope you enjoy that one as much as you've enjoyed this one. Cheerio!